the volume a little bit.
Mm-hmm.
I'm going to introduce you.
Darn.
Hello, everybody. My name is Mario Romero. I am the Associate Director for Seminars and Workshops here at Digital Futures. I'm also an Associate Professor in Computer Graphics and Visualization at KTH and the National Technical Manager at IFRS, the National Infrastructure for Data Analysis and Visualization. Today I'm going to present Renan Guarese, who is a postdoc working with Digital Futures, with AstraZeneca and KTH on a project that we have recently started. Perhaps Renan will say a little bit about that, but today he's here to talk about the work that he did towards the end of his PhD on augmented reality guidance. With that, we're ready to get started. Thank you.
So hi everyone, my name's like Mario said, it's Renan Guarese. I'm somewhat of a new postdoc here at KTH with the Digital Futures program, and today I'll present a bit of what I did throughout my PhD thesis, which was titled Augmenting the Dark, Exploring Assistive Microguidance in Sonified Mixed Reality, for which I was supervised by Professors Deb Paulson and Fabio Zambetta at RMIT in Melbourne, Australia. So prior to that, a bit about who I am. I'm originally from Brazil. I did both my bachelor's and master's in computer science back at the Federal University of Rio Grande do Sul, during which I did internships and sandwich programs in the US and also here in Sweden. So I got to contribute with a handful of universities thus far. I've been working with augmented reality since my bachelor's, where I worked as a developer for an educational AR app about physics simulation for high school kids. Later on, I started doing research within human-computer interaction for my thesis, usually working with data visualization in AR, but having also collaborated in projects involving virtual reality, haptics, assistive technology, sonification, and even digital empathy. In 2020, I began my PhD program at RMIT in Australia, where I joined a project to work on making AR more accessible for visually impaired people. So as an inspiration to my PhD topic, I would always refer back to 1989, when an exhibition named Dialogue in the Dark began to run internationally as a visual impairment awareness experience. There, visitors would face absolute darkness while performing daily activities, such as visiting a coffee shop in a specially designed darkened room, while being guided by visually impaired employees. More recently, researchers have been claiming that the responsibility of addressing disability should be placed on everyone collectively, including technology designers, while others have claimed VR to be the ultimate empathy machine, although perhaps that can be too bold of a statement for other researchers, especially within cognitive sciences. In that line of thought, by working together with a visually impaired researcher during its conception and development, and combining concepts from other related projects, my work explored augmented reality experiences that allow users to explore the dark in different manners, always being guided by sound. Through this, we managed to empower people, both visually impaired and sighted alike, with accurate guidance methods and to elicit a sense of empathy with people who are visually impaired. Along with these AR experiences, we performed 3 user experiments to try and measure the actual effects that they might produce on people's performances and emotional responses as well. So as a general exploration of related works in the literature, we gathered some key points that guided our research. Regarding audio guidance in AR devices, research is usually more focused on either outdoor scenarios and obstacle avoidance tasks, rarely exploring close-range navigation, especially within a three-dimensional context. In this sense, we decided to narrow that gap, focusing on spatialized sound and its components, since immersive environments can supply users with sensorial cues that can empower virtual experiences with lifelike features. In order to guide user perception into experiencing situations from another person's perspective, self-representation in virtual reality has been explored and manipulated, usually in an effort to embody diverse conditions and traits like a different gender, ethnicity, physical stature, mental illness, and disabilities. However, no quantitative metrics have been applied for emotional responses thus far. Focusing on blindness simulation experiences, both commercial and academic works have been implemented in VR, such as immersive documentaries, games, and other entertainment experiences. As for immersive asymmetric collaboration, sound has been very briefly explored, strictly in combination with visual cues, as to indicate the general direction of a target, so not really targeting visually impaired users or under a strict no visibility condition. This initial exploration of the literature brought us to three different main research questions which permeate the same theme: augmenting the dark with audio methods. So the research questions that guided us through this research were: the first, are BVI, by BVI we mean blind and visually impaired, so are BVI people's performances affected by different sonification patterns in 2D, hand-based microguidance? The second one, can sighted people's empathy with BVI people be affected by an embodiment of different AR experience? And finally, the third, are people's performances affected by different vertical sonification patterns in 3D hand-based microguidance in low visibility scenarios? In order to answer these three questions, we proposed, implemented, and conducted 3 user studies, which also led to some publications, the main ones being highlighted here. I'm going to talk through each of them in the next slides. Starting us off with our first experiment, the idea was to evaluate different combinations of audio attributes in a hand-based guidance interface. Since we did it in the middle of the pandemic, we decided to run everything remotely, so you would only require equipment most people already had at their disposal, such as a computer, headphones, and a mouse, which served as a 2D hand tracking device. Here, people are expected to move the mouse around and listen to different sonification methods. Audio cues would guide them to find a particular point in the 2D space without any visual feedback. This test is meant to understand how different sonification methods, be them based on pitch, spatialization, tempo, harmonics, and etc., how these can affect the user performance in navigation tasks. We have a little video here with the use cases that we were presenting. And come to think of it, I'm not sure I shared the sound in the Zoom presentation, so I'll try to do that now quickly. If I can find it. Oh, it's here. I need to share my audio, but I'll mute myself. So hopefully, let's try. Where's my other screen? It's here. Let's see if this works. No, it's not sharing sound, but I guess I can talk through it. It's not a problem. So here the person is being guided by an audio interface, which is basically doing beeps, like beep, 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 that kind of thing. So they're searching for a stove. So it's basically 2D guidance because you're only walking around a kitchen environment. Here they're looking for a place to sit in a park. So we're basically mixing up different audio concepts in this 2D scenario, right? So let me get back to my presentation here. That was me presenting this work in Canberra, in Australia, back in 2022. So our user experiment had its ethics project approved by RMIT's ethics committee. Same as with the other ones, of course, with the main difference that this one was being run fully remotely. Talking through it quickly, each user went through target finding tasks with their mouse while listening to our sonification methods guiding them, one at a time, of course, with several repetitions per method, and with all of their orders counterbalanced, which is important to avoid learning bias. So in this one experiment, 47 people participated, including 9 who were blind or visually impaired, ages 18 to 67. Here are the graphs for the quantitative results. Usually I'll go in depth about these, about the observed effects of each modality. But for the sake of today, I can summarize by saying that we found very different accuracy results with the different methods, and they were more accurate, especially when using stereo or spatial sound and tempo to convey the 2D plane. So we basically tested different combinations of these different aspects of sound, and we came to the conclusion that these were the most accurate. Regarding self-reported assessments, we used the NASA the NASA test load index to evaluate workload in different attributes such as mental demand and perceived performance. Higher scores here mean higher demands. From this graph, we can notice how the most simple method, the first one there, PO, which is pitch only, it had remarkably lower scores than most, followed by both of the methods that focused on spatial sound. There is the second one and the fifth one, SP, which was spatial pitch, and SAP, spatial alternated pitch, so involving stereo and tempo as well as pitch. Summarizing the findings of this section, we noted that the spatial audio techniques proved their value, which showed the advantages of adding a spatiality component to audio guidance systems. Pitch only, although being the simplest method, which was evaluated with outstandingly low workload demand, which would usually be a good thing. However, we noticed that its high perceived performance scores did not correlate to the user's actual performances, which were quite inaccurate, actually, making this a very misleading method, not being suitable for using tasks that require precision. Now moving on to research question number 2, which focused on developing empathy via embodiment of difference. This study was presented and published at IEEE last year, and it was one of the runner-ups for best paper there. And that's me presenting it in Shanghai, in China, at the beginning of last year. As to validate this research in the first place, we provided to the Australian BVI community with a questionnaire regarding their opinions on the need of empathy evoking experiences, as whether they believe those to be beneficial or not, because obviously it could not bring any value to them. Based on their feedback, we believe this work would explore a valuable gap that is in line with the BVI community's beliefs, and it has a potential outcome not solely on increasing empathy across society, but also on the development of novel assistive technologies in the future, which is what was one of the things we asked them. Regarding the experiment scenario, we had blindfolded participants perform a generalized task while relying on a proposed assistive technology, which was based on the previous experiment. So the previous audio interface that we tested. Basically, they had to perform close-range navigation and object handling tasks in a kitchen environment while listening to dynamic audio guidance methods calibrated and played by a HoloLens 2, which is an augmented reality headset. The participants would listen to audio instructions on how the experiment and the guidance worked and interact with it via voice commands. People went through several trials of trying to place a small plastic token into different paper plates spread around a large cupboard, as we can see there, being solely guided by this audio feedback and their own sense of touch. So they were allowed to touch around to feel the environment. So in order to effectively measure emotional response from the users, we adapted a questionnaire highly used to measure sympathy and empathy responses. These questions were originally meant to measure the public response while watching advertising pieces in the form of video. So we had to adapt them. We adapted the phrasing of all of its statements into 3 different versions. The first one was in the form of a survey for the BVI community as to assess their overall views on sighted people's emotional response towards themselves. The second one served as a pre-test for the sighted people participating, assessing their emotional response towards visually impaired people based on their overall life experiences, so their past experiences. And finally, a third one, which was a post-test to be applied after the experiment was done, to assess what was their emotional response towards that same community during the experiment, so when they were embodying having that condition. So yeah, while embodying a similar condition, relying on assistive technology and performing a generic day-to-day task, such as using a kitchen. Once the experiment was set up, we invited a visually impaired expert in digital accessibility to perform the trials and suggest any changes to the protocol or the experience itself. Based on their feedback, we made several changes to the hypothesis, phrasing of the questions, and the future of our research as a whole. Regarding the volunteers to participate, we had in total 97 people participating in the survey, out of which 20 had low vision or were totally blind, so the rest were sighted people. In the in-person experiment later on, 15 people volunteered to participate. So now, to look at it first, in the comparison between BVI people's perceived assessment to sighted people's self-reported emotional responses. It gets tricky with the wording here. Regarding their previous experiences with the other demographic, so the left and middle columns here. So the BVI perception survey versus the sighted pretest. We notice an increase of a bit over 15% on the sympathy and empathy scales, which implies that people with visual impairments generally perceive sighted people to sympathize and empathize with their BVI condition less than the sighted people believe to do. Now, when comparing sighted people's pre-test to their post-test results, the middle and right, I guess it depends on where you're looking from, middle and right columns there, an increase of 16% of sympathy and 23% on empathy was noticed. This suggests that sighted people in general will feel significantly more sympathetic and empathetic to the BVI condition after participating in a similar experience to this, comparing to how they previously were. So considering our methodology and its results, we arrived to some conclusions and even limitations to this part of the work. First, regarding the disparity in the first comparison, so BVI's perception against sighted people's self-reported emotional responses. It may very well be that sighted people believe themselves to be more empathetic than they truly are. If that's the case, it may be It may be due to social desirability bias, which is the tendency to choose responses that are more socially acceptable. Although those that did not participate in the in-person experience, which was the majority, these people were completely anonymous, so we had absolutely no information about them. We didn't even see them. This bias can be unconscious, meaning that the participant would be unaware that they were responding in this biased way. The disparity could also be due to sighted people not conveying this self-reported empathy strongly enough towards the BRIVI community, or that their experiences do not involve in-person or direct communication with BVI people. So they could be talking from watching a movie, or people that they generally know and not really interact with. As to the pre and post test comparison, the results supported the idea that AR experiences can affect people's emotional response towards different lived experiences, particularly in our case, those with visual impairments, as opposed to other impairments or conditions. By using a proposed assistive technology in a real environment similar to what a BVI person may in the future have in their home, workplace, or public buildings, such as a smart home scenario, instead of purely simulational VR experience, we hope to have demonstrated a good balance between people's challenges and their abilities to pursue independence through technology, which is one of the most common downsides to digital empathy experiences. Now on to our third and final research question, which specifically looks into vertical guidance using audio. We looked into a more generalized low visibility scenario. So not targeting visually impaired people specifically now, but instead being informed by the literature on accessible interfaces for them as a means to create more inclusive interfaces for everyone collectively. The entirety of these studies' results were published on the journal Transactions on Visualization and Computer Graphics. Regarding the experiment scenario, we basically replicated the previous experiment, however, comparing multiple audio methods and measuring people's performances instead of emotional responses. But we're going to demonstrate that in a bit. That's me presenting this paper in Orlando earlier this year. You might notice that I'm wearing the same shirt in every picture, but I swear I have other ones. The audio guidance methods were based on the results from the first user experiment we ran, which focused on 2D guidance. So all guidance methods used in this experiment had the same interface for its horizontal guidance. Spatialized audio beacons coming from the current target based on the user's hand position. Dynamic tempo was also used to convey the current horizontal distance to the target, with faster tempo meaning closer distance and vice versa. Did I skip a video? No, the video is after. For the vertical distance, however, the only consensus in the literature is that pitch should indicate height. There is no standardized way to map that in an immersive and dynamic 3D context. So we designed a few options for that as to put them to the test. First, as a simple baseline, which would be the traditional way, following the traditional notion that high pitch is up and low pitch is down, we used a fixed pitch to indicate each of the 5 possible shelf heights. So in our large cupboard there, we had 5 different possible heights that the targets could be in, all being based on musical notes at different octaves. The lowest note, so the lowest shelf there by the floor, which represented B3, the musical note B3, which is around 250 hertz. That one indicated the floor level, and the highest pitch, which was D6, around 1200 hertz, indicated the top shelf. Second, to the left-hand side there, we designed a dynamic pitch version of the baseline, which we call target center dynamic pitch. In short, the mid-level of the pitch range, which is 500 hertz, can be heard precisely at target height, so precisely when the person gets their hand at the target height. If the user needs to move their hand up to find the target, the pitch will sound higher than that, higher than 500 hertz, and progressively higher the farther away it is. And if they need to move it down, the pitch will sound lower, following a cubic curve. Finally, contrary to the last two, in an effort to completely disregard user auditory memory and assess its actual necessity for audio guidance, TBD, target-based target-based dynamic pitch was designed so that you would not require users to memorize any specific audio frequency at all. Instead of following the high pitch is up notion, in this method, which is to the right of the image there, the lowest pitch in the range can be heard precisely at target height. When the user moves their hand away, either up or down, it doesn't matter, the pitch will start increasing with the distance. So instead of memorizing any pitch levels, users are expected to pursue the lowest pitch they can find instead, so they don't need to memorize one. So here we do have a small video of what the users went through in the trials. Originally, we would be able to hear the audio feedback too, but I don't know if the online people can listen to that. But this is basically how the experiment ran. And again, it's audio feedback following beeps. So it would sound, the tempo would sound faster when they're closer. So beep, 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 that kind of thing. And the pitch is controlled based on the height. I think there's a part of the video that demonstrates that, but if there's no sound, it would be a bit complicated anyway. But all of these videos are on YouTube, and they're attached to the papers as well, so it's fairly easy to find them. In total, 19 people, that's for tests, for practical tests, that's what the person would be seeing in augmented reality, but it's just to mark down the positions for the experimenter to know. During the experiments, the people were blindfolded, so they wouldn't have any visual feedback. So in total, 19 people volunteered to participate, with a bit over 60% being female, ages 22 to 50. So I'm going to skip the video because we don't have the audio anyway. So now in the comparison results between the three methods, so the two proposed ones versus the baseline, which is in the middle, we can see that the third method, TBD, target-based dynamic pitch, had the highest averages for all of the objective metrics we use to establish their performance. The overall horizontal and vertical accuracy, as well as the lowest distance from target, all being significantly better than the baseline, in green here. Considering the measured effort metrics, both proposed methods performed significantly worse than the baseline in time taken and head and hand distance traveled, both horizontally and vertically for every condition. So the baseline did perform better in effort. Finally, for the self-reported demand, TBD, to the right again, had scores which overall indicated a lower workload. So people felt like they had to work less for those ones. Considering the results now regarding the last method we tested, we note how much it improved on the baseline, despite not following the traditional notion that high pitch is up and low pitch is down. We believe that this is due to it not relying on the user having to memorize any specific pitch levels, as opposed to the other two methods. This allowed users to compare the dynamic pitch levels at runtime and thus understand if they needed to move up or down and precisely how much on either direction. The fact that it performs similarly to the baseline in several of the TLX attributes, so the workload, it can be considered a positive result since sonification researchers suggest that sound interfaces like this should be designed to be weakly intrusive in order to minimize the impact of it on the real listening environment, while at the same time being intrusive enough so that users can distinguish guidance audio from any naturally occurring sounds nearby. Regarding the target-centered method, so the other proposed method, the one that did follow the traditional notion of high pitches up, it mostly performed similar to the baseline. We believe most users had trouble memorizing the specific tones in those two methods. They were usually able to tell if they were meant to move higher or lower, but frequently not to a precise point, getting similar levels of pitch confused, which led to uncertain selections in the vertical axis and very low confidence levels. So as a bit of a bonus level, after exploring our three main research questions and by building upon the experiments we performed, we decided to explore a way to integrate the empathy and the accessibility scenarios into one novel contribution based on collaboration. So other than putting people in someone else's shoes via simulated environments, we believe that social interaction in actual guidance scenarios can also elicit empathy for the difference. This type of asymmetric collaboration between local augmented reality users and remote virtual reality users has been explored in other contexts. So basically, a task needs to be performed in a specific place, but the local people don't have the proper expertise or they need help to do it. So a remote expert can join in VR, in a virtual replica of the scenario, and guide them visually with spatial cues. That's what usually is implemented. So we try to get to the accessibility aspect of that visual scenario. So we created this collaborative accessibility, providing BVI users, so blind and visually impaired users, with situated audio guidance cues in augmented reality to make spatial pinpointing more accessible, while a remote sighted guide has access to a digital twin of the user's environment, being immersed in virtual reality. This work was presented at the end of last year at ISMAR in Sydney, Australia, where it was selected as one of the 10 finalists for their student design competition. And I would appreciate here if you notice that I do own a different shirt. In our scenario, the remote sighted guides are able to see and talk to the BVI user's avatar while using controllers to place spatial targets in the environment, which are transmitted back to the user as audio targets. In the other end, visually impaired users, beyond the same spatialized chatting system, they can hear the audio guidance methods that we explored earlier in the presentation. Here we have a small video again. This one is, the audio is not too important because it's from the VR perspective. So basically the remote guide can see the local BVI person, an avatar representing them, so where they are. They can talk to them asking what they need. So in this case here, the person wanted to find a tomato, which was in the balcony. So the person there, we can see their head and the hands. They're following the spatial audio methods to find the tomato there. And finally, they get it. So this is just a virtual twin of the kitchen scenario. I casually called this a bonus level in this thesis since we haven't yet performed user experiments in this collaboration scenario. So I left it as a minor system contribution as opposed to an evaluation, which we hope to do in the next opportunity. So to conclude, we believe our sonified AR experiences pushed the current boundaries in AR by creating empathy-provoking experiences for the embodiment of difference, while also shedding light on including people who are visually impaired in the augmented reality paradigm via accessible interfaces that can also be used by sighted people in low visibility conditions. As for the future, the aim of this project is to collect data on the implemented collaboration scenario with paired evaluations of visually impaired people and their partners or friends as a way to explore the socialization aspect of guidance and empathy. By observing the use of these by the visually impaired community, we intend on optimizing our guidance methods to the community needs, hoping to pave the way for accessible applications in AR, which is expected by experts to take over user interfaces in the near future. If I have one more minute, I would like to acknowledge the huge contribution of Dr. Ron van Schindel, who unfortunately passed away nearly 2 years ago. Ron was my supervisor from the start of my PhD. He was the one that originally recruited me and who single-handedly pioneered research at RMIT to focus on next-generation accessibility efforts, and without whom I'll never be here today. So thanks everyone for listening, and I'll be here for any questions.
Could you do me a favor and make the angle of the camera wider so it includes both sides, please?
Of course, yes. Maybe a zoom out?
Yeah, there's a preset that says, I think, 2 speakers. One on the left, one on the right.
Oh, yeah, yeah. 2 speakers. Okay, there we go, yeah.
Excellent. All right, so I can turn off my camera. Can people hear me at home or at your offices? Yes, good. So you're free to please ask questions through the chat. That's fine, and I will go ahead and read them. But you're also free to turn on your microphones, turn on your cameras if you want, and join the conversation. I have a number of questions, but please don't let me go first. Anyone? Anyone from the audience here? Let's start at the end. So your bonus question.
Mm-hmm.
So if you go back just a couple of slides, actually,
good representation.
Yeah, go forward a little.
Yeah.
I was wondering when we were watching the video.
Oh yeah.
Like here, I was trying to catch if the person in physical reality has a controller.
They do there, yes.
Okay, so that's how you're tracking their hands.
Yeah, yeah.
So you're not using some kind of inside-out hand tracking like the Quest.
Yeah, it does work in the same sense because the headset we used there was the Quest Pro, so it does have hand tracking.
Yeah.
And it's pretty much one-to-one. You can just disable the controllers and have that in place. But just because it was a very the Pro had been out for maybe a month. So we wanted to demonstrate it in more of an understandable condition for everyone because it wasn't as popular yet. Yeah.
Right.
But since then, hand tracking has become better and better. Yes.
And then here you have a significant difference in that you have a human.
Yeah.
Who may start speaking. Even if it's not part of the protocol, they may say, oh, no, a little bit to your left.
Exactly, yeah.
Which is so much different than just the audio cues. How does that inform your design study?
Yeah, exactly. So that was one of the reasons we decided not to proceed with experiments here because it, in my opinion, it pretty much generates a whole new thesis. And actually, I'm glad to inform that someone else is picking up that thesis back in Australia, so that's very good. So yeah, it is very important because the social aspect comes into play, right?
Right.
And that's what one of my main suggestions was to have the people, the visually impaired people participating, bring in either the partners or a friend or someone who knows them, so that we can do more controlled experiments in the sense that it's always going to be people who know each other. On the other hand, we would need to isolate one of the variables, right? So either we isolate the guide or we isolate the visually impaired person to get their perspectives from different ends, and then we need to really do a on the rails experiment And that's not really the point. Like, although we get better data in that sense, but then you lose all of the qualitative aspect, which is the
Right.
yeah, definitely the most interesting in a social experiment like this.
You could find a middle ground.
Mhm.
And now we're speculating, but since if no one has any other questions, feel free to speculate.
Yeah.
You can find a middle ground where you gamify it to an extent. So you give
Yeah.
people cards,
Mhm.
and the cards are the statements they can make at a particular moment.
Sure.
So it's not completely on rails.
Mhm.
It is on rails, but with multiple tracks.
Yeah.
So you're giving a script to people who are giving guidance
Mhm.
to their guides. Also, it occurs to me that you could put in there an artificial guide. So you could put
Absolutely.
in there some kind of large language model.
Yeah, like an AI. Yeah. Mhm.
That has an idea of where the target is
Mhm.
and will always generate the same text for that target, and only if it is prompted, for example.
Yeah.
So then you have, in a sense, you could measure different levels of sociability.
Absolutely.
Where AI is more sociable than just a beep.
Mhm.
So something that is generating
Yeah.
voice.
But
So
less than a human. Yeah.
but less than a human, exactly. So you could have it on a gradient,
Yeah.
and then sort of measure the impact of the different levels of the sociability gradient.
Absolutely. Yeah.
I think it's super cool.
Yeah. Yeah. It is. It is very cool. Yeah.
It's super cool. Anybody have any questions? Otherwise, we can go back further on your slides.
Sure.
Okay, so there was a question that I had.
I think it's not moving anymore.
Yeah,
Maybe.
there it is.
Oh, it is.
So we keep going back. Yeah, let's keep going a little bit further.
Let me see.
Yep. So my question is about the 90 participants, 20 of whom were blind or visually impaired,
Yeah.
and 70 were not.
Mhm.
Did you simulate blindness? Did you blindfold them?
No, so these, so in this, let's say this part of, in this comparison, it was all based on a survey.
Yep.
So there was no experiment there. It was just people's answers to the question. But then in this end here, the 15 that did come in for the experiment, then yes, in that one, we had them blindfolded and do the experiment.
That's why they become more empathetic.
Yeah, exactly. Yeah. So that was the comparison. Yeah. So one comparison was BVI's perception of sighted people's empathy versus sighted people's self-reported empathy towards them. So we compared these two, and then we compared the 15 people that came in here.
Mhm.
We had their pre-study answers versus their post-study answers, and that's how we assessed the difference after they participated in the experiment.
Nice. Very cool. All right. Those were my questions. Anybody have any other questions? If not, thank you so much.
Thanks, Mario.
Thank you, everybody, for joining us. You have our contact information. We will publish the video online that we recorded today on the same page where the announcement at Digital Futures happened for today's seminar. If you're comfortable, we could also share your slides.
Absolutely. Yeah.
So we'll share the slides and the video soon. Thank you so much for joining us today. I will stop the recording now.